Lesson 18 Plane Geometry. Hello everyone, I'm Dennis. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me. Let's start the lesson with the learning objectives of this chapter. This chapter is all about recognizing geometrical properties. Here are the few geometrical properties that you need to know. The first one is geometrical properties of angles. Then, followed by geometrical properties of angles in parallel lines. Properties of congruent triangles, properties of similar triangles, properties of a circle, midpoint theorem, Tangent-Chord theorem or alternate segment theorem, Tangent-Secant theorem, and lastly, Intersecting Chords theorem. The first few properties you should have learned in mathematics. The few properties are geometrical properties of angles, geometrical properties of angles in parallel lines, properties of congruent triangles, properties of similar triangles, and properties of a circle. So these few properties we have learned in mathematics. In additional mathematics, midpoint theorem, Tangent-Chord theorem or alternate segment theorem, Tangent-Secant theorem, and Intersecting Chords theorem are the new properties that you have to learn. After knowing these geometrical properties, then you need to know how to apply these geometrical properties in solving geometrical problems. Let's revisit geometrical properties of angles. There are a few properties under this topic. The first one is adjacent angles on a straight line, or when you write this property in your answer, you can write this short form ADJ, angles on a STR dot line, which represent the title of this property. So this is a straight line of line PQ. So PQ is a straight line. This is the angle. We label it as A, and this is another angle. We label it as B. So, since PQ is a straight line, angle A plus angle B equals 180 degrees. The second property is vertically opposite angles, or in short form, vert dot op dot angles. So let's say this is a straight line PQ intersect with another straight line RS. So PQ and RS are straight lines. We label this angle as A, this angle as B. From here, angle A equals to angle B. Similarly, we can label this angle as C and this angle as D. Hence, we can also say that angle C equals angle D. Next, geometrical properties of angles in parallel lines. As stated in the title, these properties only apply to parallel lines. The first property is called alternate angles, or in short form, all dot angles. This is a pair of parallel lines. Let's label it as line PQ for the first line and line RS for the second line. And we can say that PQ is parallel to RS. And now, let's draw a straight line, and we label this angle as angle A. This angle is angle B. Under this property, alternate angles, angle A equals angle B. Next, let's label this angle as angle C, and we can say that angle C equals angle B because it is vertically opposite angles. And since angle A equals angle B as stated in the first property, then we can say that angle A equals angle C. And there is a name for this property, which is called the corresponding angles, and it is our second property under this topic. The short form is chord.angles. Next, let's label this angle as angle D. And since RS is a straight line, we can say that angle B plus angle D equals 180 degrees because it is adjacent angles on a straight line, which we have mentioned this property in the previous slides. And since angle A equals angle B as well, we can say that angle A plus angle D equals 180 degrees. There is a name for this property, and it is our third property under this topic, which is called interior angles, or in short form, int.angles. Congruent triangles. There are 4 ways to test if two triangles are congruent. The first way is all sides are equal, or in short form, SSS. Let's look at these two triangles. The first triangle is triangle ABC, and the second triangle is triangle PQR. To satisfy this property, AB must be equals to PR, AC must be equals to PQ, and BC must be equals to QR. If these 3 conditions are satisfied, then by SSS, triangle ABC is congruent with triangle PRQ. Do take note that the order of the letter is very important. Triangle ABC is not congruent to triangle PQR. The second way to test if two triangles are congruent is angle sides are equal. In short form, SAS. Let's look at these two triangles again, triangle ABC and the second triangle, triangle PQR. So under this property, AB equals to PR and angle BAC equals angle QPR. AC equals PQ. If these conditions are satisfied, then by SAS, triangle ABC is congruent to triangle PRQ. Do take note that the equal angle must be in between the equal sides. SSA cannot tell the congruence of two triangles. The third method to test the congruence of two triangles is two angles and one side are equal. In short form, AAS or ASA. Let's look at these two triangles again, the triangle ABC and triangle PQR. If angle ABC equals angle PRQ, the side AB equals the side PR, and the angle BAC equals the angle RPQ. So these three conditions are met. Therefore, by ASA, triangle ABC is congruent to triangle PRQ. The fourth way is right-angled triangle, hypotenuse, and one side are equal, in short form RHS. As stated in the title, it involves two right-angled triangles. Let's say triangle ABC and triangle PQR. So both are right-angled triangle. The hypotenuse are equal, which is AC equals to PR, and any of the other sides must be equal. So BC equals to QR. So these conditions are satisfied, then we can say that by RHS, triangle ABC is congruent to triangle PQR. Similar triangles. Two triangles are similar when the first condition, all their angles are equal, and the second condition, their corresponding sides are in the same ratio. These two conditions must be satisfied so that we can say that two triangles are similar. To test if two triangles are similar, we can apply any of the following similarity tests. The first is AA property or angle. Let's look at these two triangles. The first triangle is triangle ABC and the second triangle is triangle PQR. If this angle equals to this angle equals to this angle, we can say that by AA property, triangle ABC is similar to triangle PRQ. The second way is SSS or side. Let's look at this triangle ABC, and the second triangle PQR. If triangle ABC is similar to triangle PRQ, all three pairs of corresponding sides are in the same ratio, which means that AB over PR, which is this side to this side, equals AC over PQ, which is this side to this side, equals BC over RQ, which is this side to this side. There are a few properties of a circle that you need to know. The first property is angle at center equals 2 times angle at circumference, or this is the short form, angle at center equals 2 times angle at circumference. This is how it looks like. This is the center of the circle, we label it as O, and this is the angle at the circumference, we label this angle as theta. This angle is the angle at the center, and it is 2 times the angle of the circumference, hence it is 2 theta. There are a few variations of the diagram, and all the variations are under the same property. Let's imagine this point is movable and it moves at this direction. So it can move at this point and form a diameter. However, the property is still the same. The angle at the center is 2 times the angle at the circumference. And this point continue to move, and it moves at this point. Again, the property still apply, where the angle at the center is 2 times the angle at the circumference. And this point can still continue to move until move at this point. Then this angle will be the angle of the circumference, and this angle will be the angle of the center. And again, under this property, the angle of the center is 2 times the angle at the circumference. Property number 2, right angle in a semicircle, or in short form, RT dot angle in a semicircle. So, this property involves the diameter of the circle. So this line is the diameter of the circle, and this point is the center O. The diameter is the hypotenuse of a triangle where its another vertex touches in the circumference of the circle. So if this is the case where the diameter is the hypotenuse, then it is a right angle triangle. There are also a few variations where the point can move up to here and it is still a right angle triangle. And even this diagram shows the same property. The third property that you need to know is angles in the same segment are equal. Or in short form, angles in the same segment. So this is how it looks like. This angle, we label it as A, and this angle, we label it as B. They are formed by the lines where they start at the same point, which is this point and this point. So if this is the case, then angle A equals angle B. We can draw another angle where it also forms from the same point. We label this as angle C. So it is still equals to angle A and angle B. Here is another variation. This is angle A and this is angle B. So these two lines are the same length. So we can say that angle A equals to angle B. The fourth property of a circle that you need to know is cyclic quadrilateral. If it is a cyclic quadrilateral, then the opposite angles are supplementary. This is how it looks like. This is a circle and there is a cyclic quadrilateral, which means that all the vertices of the quadrilateral touches the circumference of the circle. So let's label this as A, B, C, and D. So if ABCD is a cyclic quadrilateral, then the opposite angles are supplementary. Let's label this as A and this angle as C. So angle A plus angle C equals 180 degrees and angle B plus angle D equals 180 degrees. The fifth property of a circle is a straight line drawn from center is perpendicular bisector to a chord. This is how it looks like. This is a circle with the center O, and this is the chord of the circle called AB. If I draw a straight line from O and it touches the chord AB at M, it will be perpendicular. And this point M is the center of AB. So we can write here that OM is perpendicular to AB and M is the midpoint of AB. The next property number 6, chords which is equidistant from the center are equal. This is how it looks like. This is a circle with the center O, and this is the chord AB. Similar with property number 5, I draw a straight line from the center O touches the line AB at point M, and it is perpendicular to line AB. I have a second chord, which is chord CD. I draw another straight line and touch the chord CD at point N. So they are perpendicular with the chords. If OM equals to ON, which means that the distance, perpendicular distance of CD and AB from O are the same. Therefore, we can say that AB equals CD. Property number 7. A tangent to a circle is perpendicular to the radius drawn to the point of contact. So here's how it looks like. This is a circle with a center O. This is the tangent line AB touches the circle, and when I draw a straight line from the center O, it touches the tangent AB at point P. From here, we will find that line AB or the tangent AB is perpendicular to the line OP. This property can extend to another variation. Let's say this is a circle with the center at O, and we draw a radius and touch point A. So here is the tangent, and we do the same thing. This is another line and touches point B. We draw another tangent. So this is a right angle, so it means that OB is perpendicular to the tangent. So these two tangents meet at point P, and we can use a straight line to join point OP. From here, we can say that OP is the common side. So since OA and OB is the radius of the circle, so OA equals to OB. By RHS property, we can say that triangle OAP is congruent to triangle OBP. Therefore, the length AP equals the length BP. Hence, angle APO equals angle BPO, and angle AOP equals angle BOP. From here, we can say that OP is the angle bisector of angle APB and angle AOB. Midpoint Theorem. Let's look at this diagram. This is a triangle ABC, and this is the point D. Point D is the midpoint of AB. Therefore, the length of AD equals the length of BD. And this point is point E. Point E is the midpoint of AC. Therefore, the length of AE equals the length of EC. If this is the case, then when we join the line DE, we can see that triangle ABC and triangle ADE are similar triangles with the side ratio of 1 to 2. Therefore, DE equals half BC, and DE is parallel to BC. Tangent-Chord theorem or alternate segment theorem. Here is a diagram. This is a circle, and this is a triangle ABC. Triangle ABC is inscribed in the circle. Here is a straight line DE. And DE is the tangent of the circle at point B. If this is the case, then let's look at this angle ABD and this angle ACB. So angle ABD will be equals angle ACB. Similarly, this angle CBE and this angle BAC. Angle CBE will be equals angle BAC. Tangent-Secant Theorem. This is a circle and this is a straight line AB touches the circle at point C. We can say that AB is a tangent to the circle at point C. Here is another straight line PQ. This line PQ is a secant to the circle where it intersects tangent AB at point R. Also, the line PQ cuts the circle at points X and Y. If this is the case, then Rx times Ry equals Rc squared. So this is Tangent-Secant Theorem. Here is the proof of Tangent-Secant Theorem. First, we draw a straight line joining point C and Y, and another line joining point X and C. And let's look at this angle. We know that angle XCR equals angle XYC because based on alternate segment theorem which we have discussed previously. Also, angle XRC is a common angle. Therefore, by AA property, triangle CRX is similar to triangle YRC. Hence, the ratio of the sides Rx over Rc is equal Rc over Ry. And we cross multiply, we get Rx times Ry equals Rc squared. The last theorem that we want to talk about will be intersecting chords theorem. Here is the diagram. We have a circle, and this is chord AB with another chord CD. So chord AB intersects chord CD at point R. Based on intersecting chords theorem, AR times RB equals CR times RD. Here is the proof of intersecting chords theorem. First, we want to join point A and C with a straight line and point B and D with another straight line. From here, we know that angle ACR equals angle RBD because it is angles in the same segment. Also, angle CRA equals angle BRD because it is vertically opposite angles. So by AA properties, triangle CRA is similar to triangle BRD. Therefore, we can form the ratio of the side RA over RD equals RC over RB. Then we cross multiply, we get RA times RB equals RC times RD. We have learned all the properties that we need to know. Now, let's apply these properties. We will start with proof of congruent and similar triangles. Here is an example. Look at this diagram. A circle passes through 6 points A, F, H, B, C, and G as shown in the diagram. D and B are 2 points on AE such that AD equals DB equals BE equals DF. GCE and FDC are straight lines. A. Prove that 1. Triangle ADF is congruent to triangle CDB. 2. Triangle GEA is similar to triangle BEC. B. Find the ratio of GA to AF. Here is the solution. For A, part 1, this angle equals to this angle. Hence, angle DAF equals angle BCD because they are angles in the same segment. Given AD equals DB, and this angle equals to this angle, which is angle ADF equals angle CDB because they are vertically opposite angles. Therefore, by ASA, triangle ADF is congruent to triangle CDB. For part 2, look at this angle. This angle is angle CEB, which is common angle. And look at these two triangles. We can say that angle AGC plus ABC equals 180 degrees because they are opposite angles in cyclic quadrilateral ABCG. Therefore, angle AGC equals 180 degrees minus angle ABC. And we look at this angle, we can say that angle CBE plus angle ABC equals 180 degrees because they are angle on a straight line. Hence, angle CBE equals 180 degrees minus angle ABC. Therefore, angle AGC equals angle CBE. By AA property, triangle GEA is similar to triangle BEC. Solution for part B. We know that triangle ADF is congruent to triangle CDB. Therefore, AF equals BC. We also know that triangle GEA is similar to triangle BEC. Therefore, we can form this equation, which is GE over BE equals GA over BC equals EA over EC. We start from this equation, GE over BE equals EA over EC. Then we cross multiply, we get GE times EC equals EA times BE. And from the given information, AD equals DB equals BE equals DF. The length of EA is 3 units and the length of BE is 1 unit. Therefore, it is 3 units times 1 unit, which gives us GE times EC equals 3 units. From here, EC equals 3 over GE. Next, we look at this equation, GA over BC equals EA over EC. EA is 3 units and EC is 3 over GE. Therefore, the equation becomes GA over AF equals 3 over GE, which gives us GA over AF equals 3 times GE over 3, and we can cancel the 3. We get GA equals AF times GE. Shown. Now, you can try this similar example yourself. In the diagram, BC is the diameter of the circle. Y is the midpoint of AC and angle AYX equals angle ABC. AW, YZ, and BC are 3 parallel lines. BW is tangent to the circle at B. Prove that 1. Triangle AYX is similar to triangle ABC. 2. AB times ZXY equals BC times AY. 3. 2. AB times AX equals AC square. 4. AW square plus BW square plus AC square equals BC square. You can pause the video and try to solve it yourself. Here is a solution for part 1. Given that angle AYX equals angle ABC, which means this angle equals this angle. Also, look at this angle. Angle BAC is common angle. Therefore, by AA similarity test, triangle AYX is similar to triangle ABC. Proven. Part 2. Since triangle AYX is similar to triangle ABC, hence we can form this equation AB over AY equals BC over XY. When you cross multiply, we get AB times XY equals BC times AY. Hence proven. Part 3. Given that Y is the midpoint of AC, therefore AY equals half AC. And since triangle AYX is similar to triangle ABC, we can form this equation, which is AB over AY equals AC over AX. And we cross multiply, we get AB times AX equals AC times AY. Now we substitute AY with the equation AY equals to half AC, and the equation becomes AB times AY equals AC times half AC. Rearrange this equation, we get 2AB times AX equals AC square. Hence proven. Solution for part 4. Given that BC is the diameter of the circle, therefore angle BAC equals 90 degrees because it is right angle in a semicircle. So triangle ABC is a right angle triangle. From here, we can apply Pythagoras Theorem, where AB square plus AC square equals BC square. BW is tangent to the circle. Therefore, angle OBW equals 90 degrees, which is this angle. AW is parallel to BC. Therefore, angle AWB plus angle OBW equals to 180 degrees, which because it is interior angles. Hence, angle AWB equals to 90 degrees, which is this angle. And this proves that triangle AWB is a right angle triangle. By Pythagoras Theorem, we form this equation AW square equals AB square equals AW square plus BW square. Therefore, AW square plus BW square plus AC square equals BC square. How we get this? By substituting this equation AB square into this equation. Hence, we get this equation. Proven. Let's prove plane geometries with Midpoint Theorem. Here is an example. The diagram shows a quadrilateral HIJK with L, M, N, and O being midpoints of HK, HI, IJ, and JK respectively. Show that LMNO is a parallelogram. Here is the solution. First, we draw a straight line joining points J and H. Here's the line. Then, from triangle HIJ, M is the midpoint of IH and N is the midpoint of IJ. Hence, we can draw a straight line joining these 2 points. Here's the line. Then, by midpoint theorem, MN equals half HJ and MN is parallel to HJ. Then, from triangle HKJ, L is the midpoint of HK and O is the midpoint of KJ. Hence, we can draw a straight line joining these 2 points. And here is the line. By midpoint theorem, LO is equals half HJ and LO is parallel with HJ. Therefore, LO equals MN. And LO is parallel with MN. Next, we repeat the same process by drawing a straight line joining points I and K. And here is the line. From triangle HIK, M is the midpoint of IH and L is the midpoint of HK. Now we join these 2 points, M and ML. By midpoint theorem, ML equals half IK and ML is parallel with IK. Similarly, for triangle IKJ, N is the midpoint of IJ and O is the midpoint of KJ, and we can draw a straight line joining these 2 points. By midpoint theorem again, NO equals half IK and NO is parallel with IK. Therefore, we can say that NO equals ML and NO is parallel with ML. So in conclusion, since there are 2 pairs of equal and parallel sides, LMNO is a parallelogram. Now you can try this example yourself. In right angle triangle PQR, O is the midpoint of PQ. A perpendicular line drawn from S meets PQ at O. Prove that 1. S is the midpoint of QR. Triangle OQR is isosceles. And the vertices of triangle PQR are points on the circumference of a circle with center O. You can pause the video and try to solve it yourself. Here is the solution. 1. Angle QSO equals angle QRP, which is 90 degrees. Therefore, SO is parallel with RP because they are corresponding angles. Given that O is the midpoint of PQ, by midpoint theorem, S is the midpoint of QR. 2. SO is perpendicular to QR and S is the midpoint of QR, which satisfy the isosceles triangle property. Therefore, triangle OQR is isosceles. 3. We know that angle QRP equals 90 degrees and O is the midpoint of PQ. By applying the property of right angle in a semicircle, the vertices of triangle PQR are points on the circumference of a circle with center O and the radius is OQ and OP. Now, let's prove with Tangent-Chord theorem. Here is an example. The diagram shows a triangle ABC inscribed in a circle and xy is a tangent to the circle at A. Given that AC bisects angle BAY, prove that 1. Triangle ABC is isosceles. 2. Triangle AYC is similar to triangle BYA. Here is the solution. 1. By Tangent-Chord theorem, angle CAY equals angle ABC, which means this angle equals to this angle. And AC bisects angle BAY, therefore angle BAC equals angle CAY, which means this angle equals to angle CAY. Therefore, angle BAC equals to angle ABC, which satisfy the isosceles triangle property. Therefore, we can say that triangle ABC is isosceles. 2. We know that angle CAY equals angle ABC. And angle BYA is the common angle, which is this angle. Therefore, by AA similarity test, triangle AYC is similar to triangle BYA. Now, you can try this example yourself. In the diagram, AX is a tangent to the circle at point X and AX is parallel to BY. Prove that 1. Triangle XYZ is similar to triangle XBY. 2. XY squared equals XB times XZ. You can pause the video and try to solve it yourself. Here is the solution. 1. By Tangent-Chord theorem, angle AXZ equals angle XYZ, which is this angle equals to this angle. And from the diagram, AX is parallel to BY. Therefore, angle AXZ equals angle ZBY, because it is alternate angle. And this is the angle. Therefore, angle XYZ equals angle ZBY. And angle YXZ is common angle, which is this angle. Therefore, by AA similarity test, triangle XYZ is similar to triangle XBY. For part 2, from similar triangles XYZ and triangle XBY, we can form the ratio which is XY over XB equals XZ over XY. Then we cross multiply, we get the equation XY squared equals XB times XZ, which is shown. Now, let's apply Intersecting Chord Theorem and Tangent-Secant Theorem. Here is an example. The diagram below shows a semicircle with center O and diameter AC. Point B is the midpoint of OA. Point F and E are points on the circumference of the semicircle such that angle ABF equals angle EBC. A tangent of the circle at point C meets the BE produced at point D. A. Show that 1. AB times BC equals FB times BE. 2. BD square minus ED square minus 9AB square equals ED times bracket FB plus BE. B. Given that angle DCE equals 18 degrees, find the value of angle CFE. State the reason. Here is the solution. A. Part 1. Let EB produce meet the circle at G. So we have to complete the diagram, becomes a full circle, and extend the line EB. This line EB produce meet the circumference of the circle at point G. Angle ABG equals angle EBC because it is vertically opposite angle. So here is the angle. And it is also equals ABF because we know that angle EBC equals angle ABF. Therefore, BG equals BF. By intersecting chord theorem, AB times BC equals BG times BE. Hence, AB times BC equals FB times BE. Shown. Solution for A part 2. Triangle BCD is right angle triangle because the radius OC is perpendicular to tangent CD, which is this angle. Therefore, BD square equals BC square plus CD square because we apply Pythagoras Theorem here. And we can say that ED times DG equals CD square by Tangent-Secant Theorem. Therefore, the equation becomes BD square equals BC square plus ED times DG. From the diagram, DG equals DE plus EB plus BG. And BG equals FB, so DG equals DE plus EB plus FB. And now we update the equation. BD square equals BC square plus ED times DE plus BE plus FB. Then we multiply inside, we get BD square equals BC square plus ED times DE times plus ED times bracket BE plus FB. We get, and rearrange the equation, we get BD square minus BC square minus ED square equals ED times bracket BE plus FB. Given that B is the midpoint of OA, therefore BC equals 3AB. Now the equation becomes BD square minus ED square minus bracket 3AB square equals ED times bracket BE plus FB. Then it becomes BD square minus ED square minus 9AB square equals ED times bracket BE plus FB. Solution for part B. We can join and draw the triangle FEC. From here, CD is the tangent, then angle ECD equals angle EFC. So by alternate segment theorem, angle CFE equals angle DCE, which is equals 18 degrees. Now you can try this example yourself. In the diagram, A, B, C, and D are points on the circle. AT is a tangent to the circle at A. BDT is a straight line such that BD to DT is 3 to 2. AC meets BD at E such that BE to ED is 2 to 1. A. Show that triangle ATD is similar to triangle BTA. B. Prove that AT squared equals TB times BE. C. Prove that AT squared equals 2BE squared plus AE times EC. You can pause the video and try to solve it yourself. Okay, now let's discuss about the solution. For part A, this angle equals to this angle, which is angle DAT equals angle DBA because it is alternate segment theorem. This angle, which is angle ATD, is a common angle. Therefore, by AA similarity test, triangle ATD is similar to triangle BTA. For B, AT squared equals TD times TB because it is Tangent-Secant Theorem. Given that BD to DT is equal 3 to 2. Now let's label on the diagram. BD is 3 units, DT is 2 units. And BE to ED is 2 to 1. So BE to ED is 2 to 1. From here, we can see that both BE and DT are 2 units. Therefore, BE equals DT. Substitute this into the equation. AT squared equals TB times BE. Proven. For C, from part B, we know that AT squared equals TB times BE, and TB is BE plus ED plus DT. Therefore, the equation becomes AT squared equals BE plus ED plus DT times BE. We multiply the BE into the bracket, we get AT squared equals BE squared plus ED times BE plus DT times BE. ED times BE equals AE times EC because it is intersecting Chords theorem. Also, BE equals to DT. So we substitute these two equations into the equation AT squared. Then it becomes AT squared equals BE squared plus AE times EC plus BE times BE. So we simplify this equation, it becomes AT squared equals 2B squared plus AE times EC. Proven. We are almost come to the end of this lesson. And here is summary where I want to share with you some tips and tricks that can help you. Proof of plane geometry is sometimes quite a tricky chapter because sometimes the diagram is confusing and you may not know where to start. So here are a few tips. The first thing that you can do is fill in any missing angles or sides which may not be given or asked by the question. They may help in solving or proving the problem. Also, look out for relationships between the various geometrical entities which allow for the use of the various theorems. For example, if any parallel lines, if it involves triangles, which could be right angle triangle, where you can apply Pythagoras Theorem. Is there any isosceles triangle, or congruent triangles, or similar triangles? Is there any line which cuts two sides of a triangle and is parallel to the third side of the triangle. If this is the case, you may want to apply the midpoint theorem. If it involves circle, then is there any angles in the same segment? Make sure that the angles are subtended by the same arc. If there is diameter, look out for a right angle. Angle at the center and angle at the circumference subtended by the same arc. Or is there any cyclic quadrilateral? Or equal chords? Or is there any perpendicular bisector of a chord? Or intersecting chords, which you can consider to apply intersecting chord theorem? Or is there any tangent to the circle? Or is there any two tangents from a common external point? Consider also tangent chord or alternate segment. And lastly, you can consider also a tangent intersect with a secant, which is the Tangent-Secant Theorem. Lastly, for some challenging problems, you may want to add one or more additional lines to the diagram so that you can apply one or more relationships as described before, which you can look at the last example that we have just discussed previously. I hope that all these tips and tricks can help you so that you are more confident in solving plane geometry questions. Alright, that's all for this video. Thanks for watching. Do you have any questions or thoughts to share? Feel free to write it down in the comment. I would love to hear from you. Do you like this video? Please don't forget to like it and share it with your friends. Until then, I will see you in the next video. Have a great day ahead.